so today we're going to look at a two proportion z-test. This particular one focuses on a study that was wondering if we added an additional anti-blood clotting drug named dipyridamole to people who are taking an aspirin therapy, would that be more effective in reducing the number of strokes in patients? So you have some information given to us here. If we take a look, we can see aspirin alone in this first group, and we can see that there were 1,649 patients who participated in that part of the study, and 206 of them had strokes. So sort of a first step might be, let's compare the two proportions from our samples and see if there's even a difference. And so I'm going to call this p hat sub aspirin, the proportion of people who had strokes in the study from the aspirin group. So we take the number who had strokes divided by the number of people in that part of the study, and we get a percentage of about, or proportion of about 0.125, 12.5%. And then let's take a look at the group that took aspirin and dipyridamole and see what the proportion is there. So I'll call that p hat sub d for dipyridamole. We have 157 out of 1,650, and if we divide those, we get a proportion of about 0.095. Okay, so it is lower. So if we look at this proportion here and compare it to the proportion of without taking this additional drug, it looks like we have a smaller proportion of people having strokes. The question is this difference you're seeing, is it big enough? So that's the question we have to ask. Those are question marks. Is there a big enough difference here to say, you know what, it's worth it taking dipyridamole? It's possible this drug might have some kind of side effects, so we'd want to be sure. Okay, so when you see a question like you do in Part A, is there convincing evidence? That means it's time to do a significance test. And so here we go. Let's go through the steps of that. First thing you want to do is define your parameters. So we're going to say that P sub A equals the population proportion of people who have strokes while taking aspirin. And that's one population proportion we care about. The second one we care about, I'm going to call P sub D, which is the population proportion of people who have strokes while taking aspirin plus dipyridamole. So here are the two population proportions we want to compare. Now, HO in any hypothesis test is always indicative of there is no difference between the groups. So we would write P sub A minus P sub D is equal to 0. That would indicate the two proportions are the same. And then our alternative hypothesis is going to be whatever we suspect is happening as a researcher. So we think that the proportion of people who have strokes while taking dipyridamole in addition to aspirin is going to be lower. So if this number I've underlined in blue is lower, we would expect this difference to be positive. So there you go. Now you have your hypotheses. After all that, it's finally time to start getting into our assumptions. So number one, there should be some kind of random assignment. Both of these groups are SRSs and randomly assigned to treatments. The second thing that has to happen is the population of all people take aspirin has to be greater or equal to 10 times the sample size in our study. which is 10 times 1649, or 16,490. So we have to assume that. Um, Normally, you'd say now, hey, the standard deviation of p hat sub a is equal to the square root of p hat sub a times 1 minus p hat sub a over n sub a. Now, that is a number, and I could calculate it, but when we're doing a two proportions z-test, we always assume that the two proportions are equal. So there's a special standard deviation formula we're going to have to use. The second thing you need to check is that the population of all people who take this other drug is greater than or equal to 10 times the sample size of people in that group, which is 10 times 1650, or 16,500. And there's really no way to check that, so we just have to, we're going to call it an assumption then. We're assuming it's true. If there was a way to check it, then we'd say we met the condition. That's the language that you use. So here you go, over n sub d. Now, like I said earlier, these two standard deviations are actually not the ones I want. The one I want is this. I want to use this formula. P standard deviation of p hat sub a minus p hat sub b equals the square root of p hat combined times 1 minus p hat combined times 1 over the number of people in the aspirin group plus 1 over the number of people in the dipyridamole group. Now, how do you get p hat combined? Remember, we're assuming the two proportions are equal. So p hat combined means we just take all the number of people who had strokes in the aspirin group, plus we take the number of people who had strokes in the new drug group, and divide by the total number of people in both groups. So let's take a minute to calculate that. Let's remind you what these numbers were. So look at the original problem. There were 206 in one group and 157 in the other. So that's going to go here. 206 plus 157. And we're going to divide that by the total of 1649 and 1650. And we get about here 11%, 0.11. So that's for p hat combined. So now we're ready to get our standard deviation, which is going to be the square root of 0.11 times 0.89 times 1 over 1649 plus 1 over 1650. So be careful when you type this in. Don't forget that square root. If you do that, you're going to get about 0.0109. So that's our standard deviation. Okay. Sounds reasonable. Final thing you need to check is for normality. To check for normality, you need to check two things. The number of people in the aspirin group times p hat in the aspirin group, and the number of people in the aspirin group times 1 minus p hat of the number of people in the aspirin group. Both of these numbers are supposed to be greater than or equal to 10. So this would be 1649 times our p hat in that case, which if you remember from the beginning of the problem, we calculated that right at the beginning. That was 0.125. There it is. While we're at it, don't forget the other proportions, 0.095. Okay, so if we go back here and we plug this in, we get 200, and guess what? This 206 number. That's what you get. Doesn't surprise you. And then this is going to be 1649 times 1 minus 0.125. And in that case, what you end up getting is the other people, other than the 206 that are in this group. So you get 1446. Well, sure enough, those are both greater than or equal to 10. So we can check those off. We need to go check this again now for n sub d times p hat sub d and n sub d times 1 minus p hat sub d, dipyridamole, what d stands for here. And you get 1650 times the proportion in that group was 0.095, and that gives you a number of 157. Again, that number is right here. Kind of see it. Okay, so In this case, you'll have 1650 times 1 minus 0.095, and that's just the remaining people other than those 157. So you end up getting 1493. Okay, so they're both greater than or equal to 10. That's a lot of work. But what we get to say now is that p hat sub A minus p hat sub D is approximately normal. So all that work, now it gets very much faster. So here we go. We're on our way to making a decision. So we draw our normal distribution. We mark off 0 in the middle because that's HO. And then we should take some time to mark off our standard deviation, which if you remember, we found that a moment ago. Let's not forget it. Here, I'll circle it for you. There it is, 0.0109. So what I'm going to do is on this graph, I'm going to mark that off, 0.0109. And I'm also going to go to negative 0.0109. And then we will add that once more. So if we add it again, we land at 0.0218, and this would be negative 0.0218. So far, so good. The final thing we need to do now is mark off our p hats, our difference in p hats. So p hat sub A minus p hat sub B, in our case, would be 0.125 minus 0.095, which when you subtract those, you get 0.03. Now this looks promising because this is really far away. If we look at our graph, you see our graph come out to the right here. 0.03 is up here somewhere. That's where that 0.03 is. And so the area beyond that is extremely small. Extremely small. Okay, so let's get a z-score and then get our p-value. So z is going to be 0.03 minus HO of 0 over the standard deviation of 0.0109. So if we do a little dividing there, 0.03 divided by 0.0109, we end up getting the following, 2.75. So we are 2.75 standard deviations above the mean. You can use a normal chart or go and use normal CDF, which is what I'm going to do. I'm going to type in 2.75. So I'll do this in a TI-84 calculator. Normal CDF. My lower bound is 2.75. My upper bound is just some huge number. My mean is 0. My standard deviation is 1. Now, some people might say, why are you using those? Because if I converted this to a z-score already, I've already taken this standard deviation into account. Or you can just think of it this way. The mean of all z-scores is 0, and the standard deviation of all z-scores is 1. When you're done here, you're going to get an answer of about 0.003. So this is an extremely small area. So what does that tell us? Well, the classic statement, since our p-value, which is equal to 0.003, is less than alpha equals, say, 0.01, or alpha equals 0.05 in this case, our z-test statistic is significant. And what that means is we're going to reject HO in this case. And that leads us to believe that this new drug that we're adding, let's remind ourselves, here it is, diprotidamol, this drug right here, did lead to a substantial reduction in the number of strokes. That this difference in proportions here we were wondering about at the beginning is a dramatic difference. So there you are. There you have it. That's the 2-portion z-test. There's one fun little thing here. It says describe a type 1 and type 2 error in this setting. So in a type 1 error means that you reject HO, but HO is true. So in this case, you would reject HO like we did. We might have made a type 1 error possibly because we ended up rejecting HO. But in fact, this new drug has no extra benefit. That's what type 1 would be. Type 1 would be the proportions of people who get strokes whether taking aspirin or aspirin plus dipyridamole is not different, even though we thought they were. So I don't know how serious of an error that is. If you consider a type 2 error in this case, though, this to me seems like the worst one. A type 2 error would be that you accept HO, but HO is false. So if you think about that here, if we accepted HO, we'd be saying we think the proportion of people who get strokes, either taking aspirin alone or taking aspirin plus dipyridamole, are the same. We would not reject that claim. We'd say, yeah, it doesn't matter. Don't give this extra drug. But in fact, HO is false. So that's pretty serious now. That means that if we had been given this new drug to patients, they would have been getting better, but we decided not to give it to them because we didn't think it made any difference. I think in this case, that'd be the worst error because you could save more people's quality of life. Okay, thanks for watching.